All right, so getting into question three, and question three provides us with three compounds, and it tells us that these compounds have been thoroughly mixed into a homogeneous mixture, and the goal is for us to conjure up a technique to remove these compounds or to separate these compounds. And so the compounds that have been provided to me are anthracene, piperidine, and oxalic acid. And the first step into these questions is to look at the properties of each of these compounds. And don't worry, I won't bore you with all the physical properties of these compounds, but I do want to point out some specific things in each compound. For anthracene, anthracene is going to be a non-polar hydrocarbon. So it's going to be very important. And the second thing I want to point out is for piperidine. Now, piperidine is going to be a polar amine, which means it is also going to be a base. And the third thing is going to be that oxalic acid is going to be polar as well, and it's a carboxylic acid, so it will be an acid. Now, as for the solubility of our compounds in various solvents, we don't really care as much as what they're just exactly soluble in, as much as what some of them are soluble in, that others are insoluble in. So that may be a little confusing. So if you look at the bottom here, you'll see that anthracene is insoluble in water and dichloromethane. On the other hand, piperidine and oxalic acid are both soluble in water and dichloromethane. This gives us a stepping stone to start our technique. And so we're going to be dissolving our three compounds in dichloromethane. Since dichloromethane is a polar solvent, it won't be able to dissolve anthracene since it's non-polar. And however, it will be able to dissolve the piperidine and oxalic acid. Well, you may be thinking, what happened to the water? Why not the water? Well, for this experiment to work, we're going to need to use an organic solvent. And since dichloromethane is an organic solvent and also does not dissolve anthracene, it's going to be the perfect solvent to do this experiment with. And so the first step is to grab a beaker. And in that beaker, we're going to add our compounds as well as the dichloromethane solvent. And when we add them in there, to make sure everything dissolves, we're going to stir the contents of the beaker. And when we do that, what we expect to see is that everything dissolves other than the anthracene. And so, since the anthracene is the only thing in the beaker that hasn't dissolved, we're going to take this beaker and we're going to perform a gravity filtration. Now, for gravity filtration, you're going to be needing a beaker, a funnel, and filter paper. And the purpose of a gravity filtration is to remove a filtrate, which is like the residue from the solvent in a solution. And so, in our case, anthracene is going to be the filtrate or the residue that stays behind. And we're going to take the contents of our beaker and we're going to pour it right into the beaker that contains the filter paper with the funnel. This is just an FYI. This is going to be a cross section of the funnel, and this is the filter paper in yellow. And so when we pour it in, what we expect to see is that all the solvent goes through except for the anthracene. It stays behind. So we're going to take the anthracene out, and to make sure that it has no impurities on it, we're just going to wash it with some water, since we already know that our solution is insoluble in water. That our compound, sorry, is insoluble in water. So now that we've removed the anthracene, we still have a solution that has oxalic acid and piperidine, and we still want to remove those. So this is where we get into a technique called liquid-liquid separation. And so liquid-liquid separation, the goal is pretty simple. We just want to separate two liquids. And there's two types of liquid-liquid separation. You have an extraction and you have washing. And in an extraction, you want to remove a component of interest, but also you want to keep a component of interest behind. So you care about both components. On the other hand, during washing, you're going to be discarding a component and keeping behind the component of interest that you want. So if we take an example, if we had sand and iron fillings, if I was interested in keeping the sand and iron fillings for a future demo, I'd grab a magnet and I'd separate them by just using the magnet to extract the iron fillings. On the other hand, if I had, if it was a washing technique and I didn't care about the sand, I just sift it away and I just keep the iron fillings, since the sand doesn't matter to me. The interest, my interest is only in the iron fillings. Now, extraction and washing are only possible because we rely on the fact that each compound will prefer one of the two immiscible phases, either a aqueous phase or an organic phase. And so the idea is if we increase the polarity of one of our organic compounds, it will then prefer the aqueous phase. So what does this mean? So we have right now a mixture of acid and base in an organic solution. So if we add a base to our solution, what do we expect to see? Well, this base is not going to react with the base. It will, however, react with the acid. And when it reacts with the acid, it will increase the polarity of that acid and cause that acid to become to prefer the aqueous phase. This is the whole idea behind the separation of two liquids. The piperidine in our example is going to be the amine, and it's therefore going to be the base. And on the other hand, the carboxylic acid is the oxalic acid, and it's going to be the acid. A lot of acids there. All right, so let's get into the technique of doing this. Separation is done in an instrument called the separation flask. And a separation flask looks like the diagram to your right. So it has a couple components. The first is going to be the plug up top, and then you're going to have a stopcock on the bottom. And so the separation flask is then going to be filled with our solution. Now, when we fill the separation flask with our solution, then we are going to add a base, NaOH. And we're going to add 40 mLs of NaOH in 10 milliliter increments. So we're going to add 10 milliliters, and then we're going to close the top, put our hands on the bottom, and then we want to mix this to increase the interactions between the base and the solution that we have inside. So we're just going to slosh it back and forth like this. We don't want to shake it too hard. So about every 4 or 5 sloshes, we're going to vent it, and then we're going to close it back up, and then another 4 or 5 sloshes, vent it, close it back up, put it on the ring stand, and let it settle down. When it settles down, we should see something like this: a separation into two phases, an organic phase and an aqueous phase. And so since we know already which one is going to be in each phase, the oxalic acid is going to be the aqueous phase since it reacted with the base, and the piperidine didn't react with the base, and therefore it will be the organic phase. But which phase is on top and which phase is on bottom? Well, to find that out, we're going to have to look at the density. If you remember, piperidine is much less dense than the oxalic acid, and therefore it's going to reside on top of the oxalic acid layer, therefore meaning the oxalic acid layer has to be the one on the bottom. And so we're going to drain out the oxalic acid layer after every 10 milliliters. We go 10 milliliters shaking, and then venting, of course, and then putting on the ring stand to separate, and then we drain it out, and we do that 4 times. And we're going to drain it into an Erlenmeyer flask. So it's going to look like this. Now, as for the organic layer, which is the piperidine, we're going to leave that layer in there, and we're going to perform a washing. We want to remove as much water as we can, as much water that may be in there. And so the way to do that is we're going to add a brine solution. And this crudely removes any water. And brine is just NaCl. And when we add brine, it's the same thing as when we added the base. We're going to add 20 milliliters, and we're going to add it in 10 milliliter increments. And when we add it, same thing, you slosh back and forth, vent, slosh a little bit more, vent, and then let it rest, and then separate it. Now, again, this time, the NaCl is going to be more polar. Not more polar, I mean, the NaCl is going to be more dense, meaning that the piperidine is going to reside on top, meaning that the NaCl is going to be on the bottom, which means we can easily we can easily take it out of our solution into any vessel that is appropriate, and discard of it as we like. And since we now are left with the piperidine left in our separation flask, we're going to take that piperidine, and we're going to pour it from the top. So from the plug up top, we're going to reduce any contaminations, we're going to pour it from the the plug up top, and we're going to pour it into a round bottom flask. And so we should go from something like this to something like this. So now that we have our compounds in different vessels, how do we retrieve them into the original form we got, which is a solid? Now, as for the organic layer, which is going to be in the round bottom flask, and it has the piperidine in it, we're going to attach that to a machine called a rotary evaporator. Now, a rotary evaporator is just a machine that's really good at evaporating the solvent in a solution. And so the way a rotary evaporator works is the round bottom flask is going to be attached to the arm of the rotary evaporator. And this arm is going to dip this round bottom flask into a heat source, which in this case is a water bath, a heated water bath. And once it dips it in, it's then going to spin this round bottom flask constantly in the warm water bath, causing it to heat up and causing the solvent to evaporate. Now, another thing that makes the rotary evaporator really good at evaporating solvents is the fact that it has a vacuum that sucks up the vapor pressure that resides on top of our solution, on top of the solvent. And by doing this, the solvent evaporates a lot faster than if it was under normal conditions. Now, once we let the rotary evaporator do its thing for a while and come back, we'll notice that on the bottom of our round bottom flask, we'll only have our organic compound that we started with. And so we're going to take this, you could scoop it out, and you could just put it into a test vial or any really appropriate vessel, which is a small beaker works as well. And yeah, and that's it for the organic layer. Now, as for the aqueous layer, you need to remember that the aqueous layer had a base added to it. Now, we need to reacidify this, this aqueous solution. And to do this, we are going to take the Erlenmeyer flask that our aqueous solution is in, and we're going to put it into an ice bath. And in this ice bath, we are going to add a HCl and a stir rock. And we're going to keep adding the HCl until all the precipitate, we're going to add the HCl slowly until all the precipitate has formed. And once all the precipitate has formed, we will then perform something called a suction filtration, which looks a little something like this. So a suction filtration has a rubber sleeve here to ensure that no pressure is lost from the suction. And also has a Buchner, a Buchner funnel up here. And this Buchner funnel, unlike a regular funnel, comes long and narrow. Regular funnels are short and wide. And finally, it has a suction flask. And this suction flask is where we'll have our suction source at, which is going to be just any vacuum, really. And so by doing this, all the solvent is going to be sucked out, and the precipitate is the only thing that's going to stay behind. And now we have the three solids as we were given at the start of the question. All right, and so how do we decide the purity of the solids that we've gotten? And so there's two ways to the two ways that we're gonna decide the purity is we're gonna start by doing a melting point test. And so if you remember, the more a compound varies from its melting point, the more impure it is. And so to do this, we're going to use a machine called an SRS Digimelt melting point apparatus. And so we're going to take a capillary, which is just a glass tube with only one side that is open. And we're going to crush some of our compounds. And we're going to add it to a capillary. Each capillary will have only one compound. And you're going to put it into this machine. Now this machine, it has a magnifying glass on it. And you could watch your compound as it's being heated, and you could set the settings on how fast you want the compound to heat. And so it would be every 30 seconds 5 degrees Celsius, and you watch it and you look for when it first starts melting to when it's fully melted and clear. So you want it to be clear from when it first starts to melt to when it's fully clear. You record that range. Now ideally that range is within 1 to 2 degrees Celsius. And like we said, the more it will vary from that range, the more impure our compounds are. The second way of figuring out the purity that we have is through an IR spectroscopy. Now, an IR spectroscopy gives us the exact functional groups that are within our compound, and it does this by shining light at the compound, and by shining the light, it sees how much light goes through, and it gives us on the y-axis the transmission percent of the light, and on the x-axis it'll give you the wave number in per centimeter. And so the way that this works is it has a little we call it like almost like an eye. And so since we have a solid compound, we're gonna put the solid compound just straight onto the machine and just crush it. We're just gonna close the thing that's like the eye, the diamond tip, and it's just gonna crush it onto the part that tests it with the light. And the reason I described to you that we're crushing it right away without mixing it with anything is because we're using an attenuated total reflectance. That's the method we're using. Other methods, you have to mix it with potassium bromide and Nugel, and then there's a bunch of things. But this method, the ATR method, makes it a lot easier for us. And so an example of an IR spectroscopy would look like this. Now, this in no way is any of our compounds, so keep this in mind. I'm just giving an example of what an IR spectroscopy would look like. So all these peaks down here are called the fingerprint. We don't care about these peaks. These peaks don't mean anything to us. Think about it as anything around 1600 and under doesn't really mean anything. So even this one at 1641 doesn't really mean anything. This is a fingerprint. We don't care about that. What we care about is these peaks up here. These peaks will tell us the functional groups that are within our compound. For example, this peak here would correspond to an OH group. And since we know the exact functional groups within our compound, since we know our compounds, no functional groups that are unexpected should show up. If a functional group that's unexpected shows up, then there has to be an impurity within our compound. All right, and so these are my references for the information.